Hello everyone, today I'm gonna give you an overview of this demo file for my new KineFX package. It's a package for Houdini, you can purchase it, there's a link down below in the description. And it's a package to create procedural skeletons in Houdini. It automates some of the things that have been a problem for me for quite a long time, and I think for quite a few people too, which comes into terms of how the skeletons can be created and how the hierarchy can be computed in a procedural way. I'm going to show you how to install the package, and I'm going to give you an overview of how the HCAs work, so maybe you can consider it purchasing it or not. So let's get into it. In order to install this KineFX package, we need to extract, and we have the folder. This is the package itself. And in order to reference it, we have this JSON file that we need to copy into the Houdini version that we have installed. In this case, I have 3 Houdini versions. I have the latest. You just open in the documents, open it, and it has like a packages folder. If you don't have this folder, you can create it. And inside, we paste our JSON from our package. I'm going to make some space, and I'm going to open it again. And what we need to do is to reference this path, right? I have it in the desktop, and I want to set it here. So in our Houdini package, I'm going to open the JSON file, and here's where you have to set your path. In Windows, at least when you copy the path like I did, you will see these red marks if you have VS Code installed. And remember that the path should use these forward slashes instead of backslashes. In VS Code, you can press Command H and we can replace a specific character for another. So here I'm going to look for the backslash and I'm going to replace it for the forward. And once it's done, now our package is pointing at the right location of our folder. And this will load the OTLs and everything that is necessary. Once that's done, you can already open in this folder of the heap, there is a demo file, and we can look at the different examples for the different HCAs. Let's take a look then at the first HCA. Delete joints is quite simple. Basically, is a collection of chained operations. It's the same as the delete joints. The only thing is that it allows you to create a chain of it. You can see here that I have different operations, and all of them can be toggled on and off. It's a little bit more of a manager for deleting joints that becomes a bit simpler. And you can delete, of course, specific joints that you want to not have, like this. And then, at least for me, it's easier to toggle on and off, having multiple in the same place. Joint noise is quite interesting. It applies rotations, scales, or translations through a noise to the rig. Here I have 2 examples of what that can be. It also uses this idea of a stacking, so you can stack multiple noises on top of each other. So for example, if I'm going to play this animation, you will see that it uses like the default. It's going really fast, sorry. So this is the walk of the capybara, and then you can overlay a noise over it. So for example, if we change the amplitude and I make it really high, it will change the specific rotations of those joints. You can select the joints that you want to affect. For example, if I only want to affect this group, I can apply to it, and then only that leg will only that leg will get affected by it. Then I also added specific weights. For example, if you only want one axis to be affected, and you want, this could be quite weird. So if you want a specific axis of the joint to be rotated, that's how you would basically target that axis. There's also a strength slider, so you are able to toggle it on or off for weights, and you will see a bit the use for that now. And this is the second example where I'm using the Electra. And that's, I did the same, but I basically created 3 different noises that are stacked on top of each other. And think of it as an additive noise. So the first noise gets added to the second, etc. That's why you can create this specific animation of the fingers. If I show to take off and toggle off the first 2 noises, you will see that the first noise is the one that drives the fingers. So technically, this is the selection of the first group. It's targeting the joints of the fingers. And then we can change it, the rotation at which they rotate, and the actual amplitude. You can also choose to animate the noise or not. This is also sometimes useful for me to pose a rig instead of actually animating it, which is quite useful. And yeah, you have like the typical roughness and all the noise parameters that you would expect. And that's when you stack on them on top of each other, you get quite interesting motions. Of course, you can add other noises, and here it's adding a rotation everywhere, but maybe I would like to add a scale to a specific, oh my God. I'm sharing, it's really fun to use these things, so I having really a lot of fun with it myself. So let's just scale the head maybe, only one, so it's not so weird. So you see that now the head of the Electra is scaling up a little bit. It's a little weird. Can change the offset so it's a bit different. Can also loop it, and can make the roughness a bit strong. So now our Electra is completely. It's kind of hilarious actually. So happy to fit the head is gonna explode maybe. Now a bit less fun but still useful. It's the joint rename. A bit like the joint delete uses the same template and the same idea where you can just rename joints by selecting them. So for example, if I want to rename this point, you can just say a new name. Oi, hello. Now our joint is called hello. Really simple. Joint supports is actually a derivative from the joints from points, but I isolated it and I made it one by itself. This is useful to add supports between joints. So you can see here, I can make a selection of a specific part of the skeleton, and this will allow me to add a specific amount of joints. You can also add noise between them, and it will keep the joints in between at the same place, so it only affects the actual supports, and then you are allowed. It basically allows you to create different variations, and the rig stays with the correct hierarchy. There is currently an issue with this one, which is also shared from the joint from points. I will show it later, and actually I can show it with this specific one. Is that the way Houdini mirrors joints is that it negates the scale. So in order to mirror an actual joint, they invert the scale to -1. And you can see it here where the interpolation between joints makes it so that the one in the middle becomes almost a scale 0. This is something that I will probably fix when I have a bit more time, because it has not been a big issue for me, at least at the moment. As I mentioned before, joints from points is actually the one that created the joint supports, and it's the one that you are allowed and allows you to create joints from points. It's quite descriptive and literal, I have to say. So what you do, you have two inputs. You have the actual skeleton, and then you input points, and then you get joints. And it connects them depending on the type of connection that you want. So by default, you have the nearest join, which means that the points will look for the nearest join of the input skeleton, which in this case is this capybara, and then it will connect and attach to the skeleton. So here I have this simple controller to change the input, and you can see that it doesn't matter what input of a skeleton you give it, the points stay the same. So it's a really interesting way to generate joins that it's not possible, at least in Houdini by default. And the same way that we could add supports in the other one, this adds the supports in our newly created joints. And you can see if we can visualize it. So here you can add these supports in between them, right? And now, for example, see in this capybara example, because this join is -1 and this is 1, is creating this weird issue between there. As I said, it's not something I've been having issues with, but just to mention that this is there and that I'm aware of it, and probably will fix it at some point. So yeah, here is the same support structure that we just saw, and you can also orient the joints from the ones that the skeleton gives, so it orients it correctly. And you also just cannot toggle supports at all and create your own skeletons from that. You can also use the centroid of the input mesh, so it will target all the joints to the centroid of the skeleton or to a single parent. You can also select where you want all these points to be targeted at. So if I want them to be here, I just press it and all of them will be targeted here. Of course, this probably will work for others, but you will see that if I have a skeleton that doesn't share the name, of course, it will disappear. So keep in mind, if you want to create procedural stuff, that it's easier to use different methods and the name. And nearest joint usually is much more general than a name. Now, in order to create most of these procedural skeletons and most of these HDAs, I use this node quite a lot. I called it rig data. It's really like rig doctor, but it doesn't initialize the transforms. And I use like the actual KineFX Python library that you can also find inside the rig doctor to extract a few values from the rig that are quite useful. Most of the times I'm using these to output the state of the hierarchy. So maybe here I can show what I mean if I see the geometry spread. So this will create attributes. It's the same as you can output from the rig doctor. And now we have a transform because a capybara has one, but it doesn't need one. And here the hierarchy state as well. This is quite handy. It tells you if the hierarchy is correct or not. So I could, for example, show that if I reverse it, I'm going to break the hierarchy and it will say 0. And even though you don't see it, now this hierarchy is not valid. And we could see it with the rig doctor. If you see it, you will get like this traversal failed of the hierarchy. And this is a way to extract this specific value in a number. And you also can get like the actual root name that before I also did not manage. So now you can get the root name quite easily, and this is used mostly for other HCAs to function. The next one is rig prune cycles. As the name says, it's going to prune the cycles of any input rig. Here is a very simple example of a circle, and then you input it to the rig prune cycles, and all it does is it opens a circle. This is the most simple example, but actually this was the most difficult one to find how to fix. So that's why I put it here as well. Another example that it's in a video, I think, is this, where I create a quite intricate mesh like this. And I create the wires, I connect them. And now this is a mesh that is impossible to use for a rig through the KineFX framework, but thanks to this node, it will solve it and it will look throughout the actual polygons and it will create a correct and valid hierarchy. You can resample the node or you can not resample. Without resampling, you keep the actual input mesh, which is sometimes really useful, where you don't have to regenerate the skeleton because you just want to fix a loop or you want to fix a cycle. And this is what this is going to do. The way it does it is that basically it iterates over the skeleton, and when it finds a loop, like you can see here, it will skip that specific mesh, and it will, well, not mesh, but actually it's a polygon, and it will script the polygon, the primitive, and it will go for the next one. It does that as many iterations as you give it, usually 100 or something, it's fine, and then it outputs the valid hierarchy. We can see if it's valid as well, for example, using a join noise. Most of the times, if it moves, means that it went good. So you can see that now, indeed, it's using like a rig because it's inheriting the noise rotations of our join noise. You can also resample it, as I had then showing. Is basically the same, but we can resample the input. So if we want it a bit more detailed or less. And then we also have this toggle to keep the largest piece, because sometimes in very specific cases you would have a leftover of a piece. And if you are creating a hierarchy, maybe you don't want that and you don't want a continuous skeleton, so that will help to ensure that you get that correct skeleton. Another example would be this curve, that it's clearly not that valid for KineFX skeleton. And that's when we input it to our rig, my Prune Cycles, it basically will go over the curve and it will open it up. So the same way you can also use curves, and you can also resample it. If you want to keep the structure of the curve, you can toggle this on and off. And if you want to resample the input, you can also do it. It does work as well for drawing curves. So here you can see this is our curve, and it also has like a very nasty curve and cycle here. And this will also say, hey, I want to take it out. This curve, for example, we need to resample it because it's completely disconnected. So this is a situation where you would like to actually use a resample. So I also made a recipe which is called rig from curve, which is the same as rig Prune Cycles, but it already includes the resample. So this one would already work directly. The same HDA actually works for these type of skeletons. So if you know, you can create a straight skeleton from a 3D object. I have this Rabbi, and this will go through it, and it will generate this geometry, which is the skeleton. But if you try to do this in Houdini, you maybe know that it's not that useful for using in KineFX. It does not have a hierarchy and it's a little tricky to do. So this will also fix it. It will go through it and create the actual rig. So I could actually check if this is also working by using a rig pose and seeing if it's actually working. So you see that now our rig is fetched. And this was like the last, it was like, if this works with this one, then I was quite happy. That was like my ultimate test. So the same does, because of the resample, it goes through it. Of course, it's an exaggeration to the max, but I was like, well, if it can work with this, I feel confident it can work with quite a lot of input meshes. So this is another example that you can check. As I mentioned, there is this rig from curve. I already showed it, but I can show it again, where you have a curve and you can call it by using rig from curve, because this will be stored in the package as a recipe, which is one of the new things added in Houdini 20.5. And this you can all directly input it to get the actual rig. And for the last one, the rig traverse hierarchy, which I'm also going to show together with the visualized joins. Because we need to visualize the joints to actually understand this one. This is the most important HCA for this package, even though maybe you're not going to use it that much, but it's the one that solves the issue of traverse hierarchy. And it basically fixes it. And it fixes it by recalculating the flow at which the joints should be going, setting a new joint, or inheriting the old joint, the root, excuse me. To visualize this, we should actually check the animation, the rig inspector, the rig tree, and here will help us to see the hierarchy of it. So right now, the root of this skeleton of the capybara is starting at the pinky toe, but that's usually not the case. If I use a null and I go from the capybara, you will see that usually it needs to recalculate. Let's see if it's, yeah, so it needs to refresh a little bit. So usually it's a C main, and from here it goes from C-cog and the pelvis and the spine, etc. And this reverse hierarchy can also be used to recalculate the location of the root. I also have the visualized joints to visualize where the root is. So here, when you see that this is selected, you will see this square. This square shows you where is the root. So this is the root from the original one. And when we traverse the hierarchy, it's now in this toe. What we could do is to completely change the hierarchy, and you will see that it doesn't break. And you will see that these tiny arrows that represent the flow of the skeleton change accordingly depending of where the root is starting, in order to make it correct. Because when our root starts in the hand, it needs a specific flow, and when our root starts in the toe, it's another one. So this is what this takes and does. And we can also set the root type by, for example, the joint name. So we could say we want the neck, or we want the, let's see, the nose. Does it have a nose? It does have a nose. So we could start from the nose. And this, another way to visualize this is with the join noise, which I use so much in order to visualize it, is because if we toggle it like this, the join noise is accumulative because it starts at the root and each rotation is inherited from the child joins. So you will see that a nice way to visualize the root is to see the one that is not moving. So indeed is the nose, right? I actually want to see how this is looking for the capybara. Sorry, 1 second. So I'm gonna bring the skeleton, bring the mesh, and I bring this noise. So yeah, that's something you could do with this. And you could change it as well randomly. So that's why I had this thing. You could see how it looks like this. It's to update to stop the timeline to get the UI. So you could change completely the root, and then it will change it for the specific root that it locates. This sometimes needs to refresh, so it's not fully accurate. So we need to get it back. So now we are here in this weird name, Scapula. Yeah. So in the right here, I have the same explained, but using the reverse. So what this does usually creates this error, right? We can visualize it here. I'm gonna just toggle it off and take out the capybara. Bye-bye. And what this does, it shows us which basically which primitives are located and rotated wrongly in its order, in the vertex order, so that they have a wrong traversal, basically. So you can see here, if it would start on the heap, it will go up, but this primitive is going down because of its vertex order, so then it gives us this error, the cycles. It doesn't mean that the geometry itself has a cycle in terms of being connected like this, right? But it has a cycle in terms of the order at which the rig is set. So this is what it saves. Once we use our rig, we are using a join to make a new root. And then if we visualize it, it solves that hierarchy. So here we can now input the rig doctor and visualize the joins, and it works. And the same as we did here, this would be the function for this. Now, quickly, the last HCA included in this package so far is this one that I called Visualize Joints. Is the same. I'm gonna close this one. It's the same as the Visualize Rig. It's not that different, but I added a few things that help me to debug quite a few things, to be honest. For example, I am able to show the root of our skeleton. It gives me a little bit more control of what join axis I want to see, so I can toggle them on and off. So if I want to debug the x-axis for rotations or for whatever purpose, it's a bit easier. I can scale it, and it just gives me a little bit more control on the visualization, as well as you can just show the joints and not the orientations, or the parent to child relationships, which can be broken by using, for example, a reverse. And then we can see like this, that now is, at least for me, was a bit easier to see it also in the primitive, instead of only having like this arrow. That's the one that comes by default with the rig visualize. And that's it. There's not much more to it. You can just set the scales for it and select the joint group if you need in order to visualize a specific layer. So this is it. This is the KineFX package, at least in its first release. I am actually having quite a few more HCAs on the way, but I felt that was a good bunch to actually put out there and have people use. And it would be great if you can download it and purchase it. And if not, it's also fine. Thanks for watching, and see you another time. Have a nice holiday if you can. Okay, bye.